Chronal Dragon. Know of any good resources for learning about Quaternions? So, I guess I would say, you know, I guess I don't know. I, there's got to be by now, but I don't know. I mean, spelling. So quaternions are really pretty simple at the end of the day. Um, a quaternion is just a way of writing a vector times the sine of half the angle and the cosine of half the angle, right? So if you think about any given rotation, oops, wow, it's been a long time. No, I did it right. Okay, I was gonna say gotta get some right hand rule in there. So if you think about any given rotation, where you have, I'm going to rotate something about a particular axis, we'll call that v, by a particular angle, theta, then the quaternion that represents that rotation is just this, right? And while there's a bunch of sort of minutia that you want to kind of work out once or whatever, to figure out how to turn those into matrices or to transform vectors by them, to actually use them once you've constructed them, and to do multiplication with them, those routines are rather rote. And so once you have those routines, as long as you can understand this, you're pretty good to go most of the time, right? Because everything else that you might want to do, you can usually figure out just by thinking of it in terms of this. Because you always know the angle of rotation, right? By looking at these two things. So if someone hands you a quaternion, and by the way, this is four elements, right? Because this is a vector, a 3-element vector, right? It's Vx sine theta over 2, Vy sine theta over 2, Vz sine theta over 2, and then the fourth component is just cosine theta over 2. So that's the quaternion, right? 4 elements, element 0, 1, 2, 3. So these come from this, and this is just a lone term, right? So if you understand this, you can pretty much do anything you want to do with quaternions from then on out. It's really pretty remarkable. If you just use your geometric intuition, you can do just about anything else you want. You want to make a rotation around an arbitrary axis? Well, this constructs it directly. If you know the axis and the angle that you want to rotate by, you just compute this. You stick the axis, and again, this axis is considered usually normalized, but there's reasons why that doesn't necessarily matter. But point being, you have this, you have this term by just computing the sine of half the angle and multiplying by the vector. That's your first 3 elements. Then you just stick the cosine of half the angle in the 4th element. Done, right? You want to do the reverse of that? Well, you know what the vector of rotation is because the first 3 elements normalized give you that axis. So if someone just hands you a quaternion, right? Qx, Qy, Qz, Qw. Someone just hands it to you and you're like, I don't know what the axis is. Well, the axis is just this. That's the axis. And if you want that axis normalized, you can just take that, vector over its own length. And there's a normalized axis of rotation directly from the quaternion, right? And you know that axis can't be 0 because quaternions, the ones that you use for rotations, are always normal, right? Because if it wasn't, you can't ever have a quaternion, that was going to be all zeros and have any rotation, right? That's not possible. So assuming that it represents an actual valid quaternion that you would ever be using, then you can just get it directly out there. And if you want to know what the angle is, well, when you do this, right, when you find this length, the length of this vector, which you're going to have to do this to divide by it, well, the length of that vector is the sine of half the angle, right? And you already know the cosine of half the angle because it's right here. So if you want to know theta, you can just plug those directly into a tan 2 because now you've got the cosine and you've got the sine of half the angle. That will pop out your theta over 2. Just multiply it by 2 and you have the angle. Done, right? everyone wins. So again, quaternions really, really simple. There's really not much to them. You can actually treat them essentially as linearly combinable things as well. So the quaternions that you care about for rotation are unit quaternions. Which is to say that they have unit length. So the length of the whole quaternion is always 1. And so in that case, you know that you can always like renormalize a quaternion. Like if someone gives you a quaternion that's not unit length, you can always just renormalize it back up. And that corresponds to a bunch of non-Euclidean geometry stuff that we could talk about some other time, but point being it's pretty easy. And the idea here is that if you want to, you can actually just take quaternions as if they were vectors, because they are actually vectors if you don't consider this constraint, the unit quaternion constraint. They are actually vectors, so you can take two quaternions in 4D space. You have to imagine this is some magical 4D drawing. And if you want the rotation that's halfway between the two, you can actually produce that. You can just add the two together. So if you have Q0 and Q1, and you want the thing that's halfway between them, you can do a bilinear blend, just 0.5, right? Or just 1/2, plus 1/2 equals some new quaternion. This is now the rotation halfway between those two, right? It actually works to use the linear compositor. Now, the thing that doesn't quite work is because these are technically a unit, they're a mapping of unit quaternions, it means that the analog would be like as if you were on the surface of a sphere or on a circle or something like this, right? Where the great arc is what you renormalize back to. So going halfway, you will get exactly the rotation that is in between those two. But if you went some other amount, let's say a quarter of the way, you will actually get not exactly the right combination between the two. It'll be slightly off because of this projection. So the arc lengths here will not be half and half, which is what they would have been, right? This will be, and this will be equal length, but these will not be, right? But that's usually very, very minor. That's usually really not that big of a deal. So for almost all intents and purposes, you can almost just treat them like vectors everywhere. That's what we did in Granny. We were the first animation system to ever do that, as far as I know. I sent out a thing in like 2001 where it's like, oh my god, guys, I like visualized all these things, and it turns out you can actually just use these as linear, and there's all these like sort of things you can do with it and blah, blah, blah. So yeah, quaternions are really not that hard at the end of the day. So yeah, just remember this and you'll be okay. Remember this and think it through. Just think it through.